This is problem 3 in chapter 10, where I have a spinning disc. This is called a grinding wheel. It's 90 kilograms, very heavy, and it's spinning at 90 RPM, and then I push on it with a force of 20 newtons in order to slow it down. That force directly doesn't cause any slowing because it's a centripetally directed force. However, it does create a frictional force in the opposite direction. And so this force slows down the spinning wheel, and we want to find out what's going on in terms of making it stop. So let's first find the frictional force, which is equal to the coefficient of friction, in this case 0.2 newtons, 0.2, sorry, times the normal force. Now, if I'm pushing down on it with 20 newtons, it's pushing back with 20 newtons, so the normal force is 20. So my force that's slowing this whole thing down is only 4 newtons, pretty small force. I also have to find the characteristics of the grinding wheel. The moment of inertia of the grinding wheel, we're going to treat it as a disk, so that's mr squared. So that equals 1/2 times 90 kilograms times 0.34 meters squared. So that equals 5.2, and the units are kilograms meters squared. Okay, now, in order to find out what's going on, we use Newton's second law applied to angular motion, in which torque equals I alpha. Our first problem is trying to find alpha, so that's equal to the torque over the moment of inertia. The torque is just equal to the friction times the radius, so the friction is applied here, and it's acting at a radius r, so r times friction equals torque. And then we also have the moment of inertia, 1/2 mr squared. Okay. When we plug this all in, we get a angular acceleration of 0.26 radians per second squared. Now, we're going to call this a negative force, a negative torque, because it actually turns this in the clockwise direction, which is a negative torque. And we'll note that the velocity is counterclockwise, a positive direction. So that allows us to understand that we're having a positive velocity with a negative acceleration, so the velocity is getting smaller and smaller and smaller until it stops. Now, the second question was, what is the angle theta that disc goes through in terms of stopping? Before we can do that, we have to convert 90 RPM into radians per second. We would multiply by 2 pi radians per revolution, and we would multiply by 1 minute per 60 seconds, so 90 RPM is 9.43 radians per second. That's the initial angular velocity. So we can use the third kinematics equation in which to find angle theta. So theta equals the final velocity squared, which is 0, minus the initial velocity squared over 2 alpha. Remember, alpha is negative. When you plug all this in, you get that goes for 170 radians. And then if I divide that by 6.28, 2 pi radians, then I get 27.1 revolutions.